Hello, welcome back to 11th grade physics with Mr. Herniter. And as you can see, I still have the hole in my ceiling. It's not fixed yet, so stand by. I'll let you know when it gets fixed, and we can all celebrate when when we're in class, when that happens. What we're going to do today is introduce momentum. Let me share the screen here. Momentum is a topic which is fundamental to physics, and we're going to be exploring, just starting to explore that today. And maybe if I have enough time, we will also talk about the OSIRIS-REx spacecraft, which landed on an asteroid last Tuesday, October 20th. Otherwise, I will get you the information about that a little bit later. It's very interesting, and I'm going to use them in a couple of problems. So stand by for that. Let's see here. Here we go. We've got a do now. There are 2 questions on it. Please take a look at that and answer it on the Google form and upload it there to the to our class website. And I'm going to be monitoring it. And when you're done, give you 2 minutes. Wow, those 2 minutes went fast. Let's take a look at the answers to the questions. All right, what is velocity? Can anybody help me on that? Velocity is, okay, Ben, what do you say velocity is? All right, velocity is speed. All right, speed, and what else? All right, Sarah, speed and, okay, you got it. It's speed and it's the direction of its motion, right? The second question is, what is mass? Right? Can someone tell me what mass is? Okay, Joni, what's mass? All right, so mass is the amount of stuff, but we gave it a specific, meaning, right? How much stuff do you have, right? And okay, Joni, you want to take another shot at it? It is, okay, that's right. It's resistance to change of the state of motion. All right. So those 2 concepts are fundamental to the concept of momentum. And momentum is what comes out of Newton's first law of motion. So we're going to take a look at Newton's first law of motion and see if I can't convince you that momentum is in there somehow. All right, so Newton's first law. It starts off pretty simply. Let's get this laser pointer working. An object at rest stays at rest, and an object in motion stays in motion. So it either stops or it keeps going, and with the same speed and direction, unless it's acted on by an unbalanced force. So let's take those apart, one by one. An object at rest stays at rest. Well, we know if we kick a ball or we drive a car, and you stop the engine on the car, or you just let the ball go, it eventually stops, right? So once it stops, it doesn't seem to move unless something pushes it. So it stays at rest unless something else comes out to it. And we say it resists moving, right? Now this second part of this, an object in motion stays in motion. Now this is something that's counterintuitive to people because we know, like I said, cars stop, balls stop, bicycles stop, everything stops. So where did they get this idea? The idea comes from the fact that in Newton's time, they were making great discoveries about the orbits of planets. comets, that sort of thing. And they could see that those celestial bodies kept going in their path without anything stopping it. So they tried to figure out why that would be up there. And they made the assumption that it's got to be the same physics up there that there is down here. So Newton came up with the idea that maybe what was happening up in the sky was what was normal, and down here we just couldn't see it because there were so many other things that were impacting the motion of the ball, right? They weren't going between planets. It was on the grass, and it had, it had friction, something like that. So an object in motion stays in motion, and it also resists changes to its velocity, kind of like an object at rest tends to stay at rest. It resists moving at all. So what do you know that resists changes to motion, right? There's something that's defined by that, and that is, anybody? Okay, I see in the chat. All right, it's mass, right? Mass is resistance to motion, right? Or resistance to changes in motion or changes in velocity. All right. And then it says, and with the same speed in the same direction. So what combines speed and direction? It's velocity. So in Newton's first law, we've got mass and velocity, and we have to figure out what the relationship between the two of them is. But the last clause, we're not going to really get to what it means until we get to Newton's second law. But let's try to take a guess. Unless acted upon by an unbalanced force, right? So we know that velocity is either zero or it's got constant speed and direction unless it's acted upon by an unbalanced force. So an unbalanced force produces what? It's got to produce some kind of what? All right. We know that the ball either rests or keeps going unless it's acted upon an unbalanced force. So that means the force has to do what to the ball? Right? Well, stop it. Anything else? All right. All right. Maybe make it go faster. All right. So what do the forces do in general? They change what? That's right. Forces change an object's velocity. And we'll exploit that more, and it's going to be where quite a lot of our physics comes from the rest of the semester. Okay, the role of mass and velocity. How do mass and velocity act together? Well, if two balls are thrown at you with the same speed, which one hurts you more if it hits you? The light one or the heavy one? Okay, the light one, hands up. How many people say light? Not too many. Heavy one? Yeah, everyone's saying the heavy one does. That's right, the heavy one. What happens if two balls are thrown at you with the same mass? All right. Which one would hurt you more if it hits you, the slow one or the fast one? Right? Okay, now everyone's got their hands raised. Online, yes, it is the fast one. Okay, so they balance each other, out. They have the same effect. The more speed, the harder the ball hits you. The more mass, the harder the ball hits you. So mass and velocity are acting together, and acting together, they're called momentum. And momentum. And the equation for momentum is not here. I made a mistake in the slides. It's not here. The momentum is defined as mass times velocity, right? Mass times velocity. So given that momentum is mass times velocity, let's go to the problem, all right? So here's the problem, and why don't you help me with it? A 50 kilogram person runs at a rate of 6 meters a second. What is their momentum? Right? Well, the momentum is mass times velocity. We talked about that, right? And unfortunately, I forgot to stick it in the slide. And then the next line, I've got an equation which kind of sort of looks like it might be related to the one above it, right? The P stands for momentum, and the mass, the M stands for mass, and the V stands for velocity. You've seen the M and V before, right? So if we plug it in, we've got mass is 50 kilograms, velocity is 6 meters per second. So what's the momentum? Okay, by that equation, it's, all right, Joni, it's, right, 50 times 6, or 300, but 300 what? Well, it's got to be kilograms times meters per second, or kilogram meters per second. That's how we read this. It turns out that you can multiply units together and you get a combination of units like kilograms meters per second. It's really kilograms times meters divided by seconds. Now that minus sign in the middle, that doesn't really mean minus. It just means they're connected. Some books use a dot to remind you that it's multiplied by each other. Others use a dash. Right? So with this as a guide, all right, I'm going to throw some problems at you. Right? Problem 1 is about the OSIRIS-REx spacecraft. It weighed about 880 kilograms, and when it was landing on the asteroid Bennu, which happened on Tuesday of last week, it was traveling at about 1.5 inches per second, which turns out to be about 0.038 meters per second. So find out what the momentum was for that. And the second one is a running person with a mass of 75 kilograms has a momentum of 525 kilograms. How fast is the person running? Right? Work this with a partner, and then we'll come back together again. And well, you submit it and come back together again, and we will talk about it. Okay, so everyone seems to be done with it and submitted. And let's talk about problem 1. Okay, now in problem 1, we've got mass times velocity, and it's 880 kilograms times 0.38 meters per second. So the answer is 33.44 kilograms meters per second. How did we do on that? All right, do you agree with my answer? I see some of you agree with my answer. Anybody have any questions on it? Okay, we'll get a chance to work on it some more. All right, let's go to problem 2. A running person with a mass of 75 kilograms has a momentum of 525 kilogram meters per second. How fast is the person running? Well, you got to manipulate this. All right, the answer is 7 meters per second. How did I get it? Well, since the momentum is mass times velocity, what I have to do is move the equation around so I get velocity equals something. The first thing to do is to divide both sides by the same thing. To get velocity by itself, I have to divide by m, so that m divided by m cancels out, but I have to do it on both sides. So the left side becomes p divided by m, or momentum divided by mass, equals, and then the right-hand side, it's mass times velocity divided by mass. The m's on the right side cancel to 1, and so what you've got left is momentum divided by mass equals velocity. You flip the sides, which you can do because they're equal. It doesn't matter which is on the left of the equal side or which is on the right. And you get velocity is equal to momentum divided by the mass. Well, that's 525 kilograms meters per second divided by 75 kilograms. So you got 7 meters per second. Right? How do you get the kilograms out? Well, it's because the kilograms up here is canceled by the kilograms there. It's kilograms divided by kilograms. Those cancel out, and you're just left with the meters per second. 7 meters per second is a pretty good clip. It's like a 4-minute mile. Okay, exit ticket. Answer this problem on your own, right? What were to happen to the momentum of the OSIRIS-REx spacecraft if both the spacecraft's mass is doubled and if the spacecraft's velocity is doubled? What would happen to the momentum? I'm not asking you to make a calculation, but based on the equation, right? Momentum is equal to mass times volume. What would that be? Okay, so fill out your exit ticket. And when you're done, come on up, hand it in to me, and you're free to leave. And next time we're going to explore momentum a little bit more along with force. All right, take care.